last class final slide that we go through these three main phases of the universe. Just see the graph below, the log scale, log rho versus a log a. So the first point around 0.1 or 2 million year, universe is radiation dominated, meaning radiation energy means relativistic particles where the rest mass is zero almost, dominated by photon, neutrino. That was the main contribution of the universe total, as we saw yesterday, because it's 1 by 8 to the power 4. And today that radiation energy density is very less, 10 to the power minus 3 or 4 times the matter, dark matter or visible matter. So then matter takes over, and in between say 0.3 million year to 8 billion year, when all the galaxy forms, everything, that is matter dominated universe. And around 8 billion years later, you can think of like when Earth just formed. That time onwards, the lambda cosmological vacuum energy dominated, and it is called dark energy dominated or vacuum dominated universe. So why we have the it is so important to know this plot, because depending on what domination of universe you are, you can approximate the universe with only that fluid. So you can actually forget about, suppose you are in matter dominated universe, you can think about, because you can actually neglect dark energy and radiation pretty much, and you get only 1% error, and then it is easier to do cosmology equation. So now with this idea, today we'll derive the epoch of matter radiation equality, how the scale factor, the expansion happens in different epoch of the universe. All these things will derive now. So today will be less talking, more of board work. You can see the whiteboard.
Yes, sir.
Okay. Just 1 second. Okay. So as I said in the last class, let's go to the full book. So for cosmology, the main thing is called the Friedmann equations. This is the main thing for cosmology. Okay. What is Friedmann equation? It is it comes from the GR equation, general relativity equations. So what is GR equation? We told last time that we will not go into the detail. G mu nu, which is basically defined as, it's a rename of this thing, R mu nu minus half G mu nu. G mu nu, small g mu nu, we know it is FRW metric for this, and this is called Ricci scalar. This is actually the equation, is 8 pi g by c square T mu nu. And T mu nu is rho minus p minus p minus p for homogeneous fluid. So this part will not go into the detail now, but those who want to know in detail will send them the notes that from here, either by calculating with Mathematica or by hand, it's a long calculation. So what is our, you can find out the Friedmann equation of cosmology. So what is actually that equation? Input, the input is G mu nu is that one, minus 1, a square, a square, a square. You can actually keep the k term, then it will be a little different. But we'll not put the k equals to 0 right now. You remember that metric has the k term also. A square t into dr square by 1 minus k r square. So if we keep k, it will be a little different. But mainly with k equals to 0, this is the metric, and t mu nu is rho minus p and minus p. So as we said that both left hand side, all the quantity in the left hand side, r mu nu is just a function of scale factor g mu nu. So is r. R also is also a function of scale factor. Scale factor means the metric. Now you can see in the metric there are only two things unknown in the metric. In the metric, unknown quantities are two things. Can you tell me what are the two things in the metric which we don't know, which will be function here? So if we somehow calculate, I am not telling you it's a GR equations of many differential equations, but there are only two unknown. One is A, T, another is, if I just said, if we keep the K non-zero. There is no third unknown in the metric. You remember? Yes or no?
Yes, sir.
Metric is how much? ds, we remember, no? The metric is, who can tell me? Minus c square
dt square.
The coefficient of the metric is what matters, because that that goes into the diagonal element, plus a square t times
ds square by 1 minus k.
dr square, dr square. This you should remember again, and then k square plus all this dot 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 r square d theta square, all this thing. Yes, there is no k here. So you can see, if you write down in the dr, d theta, d phi coordinate, the metric will also pick up at by square root of 1 minus k square term. Because if you don't put k equals to 0. So only two unknown thing in this metric is A and K. Two unknown. So now I will not go into the detail. So if once you solve the equation, you get only two equations which are very simple. So first equation you get, because these r mu nu, r, all these things are derivative. As I said, you remember last class I say it is equivalent to like a Poisson equation. Poisson equation has this double derivative term grad square phi is 4 pi g2. So like that, here you have both space and time derivative, because in GR, space and time are both treated as dimension. So you get this equation, A dot by A is equal to, square, the first Friedmann equation, 3 A dot by A square. I'll give you the exact. You got to see it? Yes? Hello?
Yes, sir.
So this is the first Friedmann equation. A dot by A square is 8 pi g rho. So see, the rho is coming from the right side, and A dot is coming from A dot. Actually, people, you can write it like this. You can, because left hand side is just, you can just erase this part. Just write here K by S square plus. So this is this you should remember totally. The first Friedmann equation. And the second Friedmann equation is A double dot. It's a second derivative equation. These are the two independent equations. You get A double dot is equal to minus, there is a minus term, 4 pi g by 3 rho plus 3p. So now you know that why pressure enters, because the metric and T mu nu has pressure term. So rho and pressure term enter, and left side here there is no k terms enters. Somehow it gets cancelled. So this is the Friedmann equation for the second Friedmann equation, which is the most important one. These are the two Friedmann equations you should remember by heart. Is it clear now? Yes. So you see, there are only, it connects the left hand side of the metric. Geometry is depend on the metric, as I said in the video yesterday. And the geometry is given by AT and the K, because if you see here, the top right corner, geometry is the distance, it's given by AT, the scale factor, and the K. If you know A and K, then all the things you know, C you know, and it is dr, they are the coordinate. They are not the independent. They are not to be solved. They are like the coordinate. How many space-time dimensions? The coefficient of the coordinate gives you the distance. Clear? Yes. So you can see that all the coefficient of the coordinates entering in the left side of Einstein's equation, that is the geometry, and right side is the matter, how much energy density you are putting. But here is one difference, that not only rho enters, but also this is also geometry in the second equation, A double dot by A, how the A is carved or velocity, because these are part of metric only, AT. But pressure also defines how your geometry will change, how A dot will change, means A double dot will non-zero or zero. So all this quantity, A double dot, A, K, they are part of the gravity. Means if you know them, then you know the space-time dynamics. So now let us write down very nicely these two equations. Again, I will write down. Actually, no, before that, so I have that equation. Okay, write down A. Can you tell me, can you remember A dot by A square? Now I am taking the K to the other side. It's very simple. 8 pi G by 3. G is the Newton's constant. Rho is basically rho total. I have not written last time. Minus K by S square. Okay. This does not come under bracket. This is the bracket. This one will be different. Okay. So this is the first equation, and the second equation is a double dot by A, there is no square here, a double dot means acceleration, minus 4 pi g by 3 rho plus 3p. This also means rho total plus pressure total. So if there are many components of the universe fluid, you have to add them. So now I'll just drop this total term. It doesn't look so good, but know that this is total. Okay. This you should know by heart. So now I will tell you for most of the cases, later I will prove that k equals to 0 from observations, not from theory. Theory may k is allowed from CMB observation. Later I will talk about it. K not exactly equals to 0, but actually very close to 0. It's basically very close to 0. This is an arrow. Okay, let me write it nicely. But we'll take k to be 0 mainly. Tends to 0 means mostly it is 0, but we don't know. There will be some error bar from observation, but this is from observation. But for theory side, we have a strong belief that k is actually 0, mainly from theory. Okay, expectations. But of course, they have to match. So if it is exactly 0, the error bars are still within that. So mostly we believe k equals to 0. So now I have some, you take your pen and paper. Okay. These are the two equations. Have you written it down in your notebook?
Yes, sir.
Yes, sir.
All of you need to write it down because I'll give you some thing to solve right now. Shall I wait or shall I move to the erase it immediately? You need to keep it in your notebook to solve something. Shall I wait or shall I? All of you have noted down?
Yes, sir.
Other people?
Yes, sir.
Okay. Yes, I need to know. Okay. Let me see. Chat box may you have to answer for all of you. Okay. Today, as there are a lot of board work I am doing, I am not talking that loud because you have to solve few things. Okay. Sometimes doing silent board work is also part of the physics.
Sir,
Yes.
in the G mu nu metric k is not there, right? Is it because we take it to be 0 or
No, if you don't take to be 0, then k will be there.
in metric?
Originally, k will come, but only from observation we find out k equals to 0. So when you do the mathematics, you should keep non-zero k. Okay.
So in the metric G mu nu k should be there.
Yes, because G mean is a function of metric, and metric has both a, t, and k term, isn't it?
Yeah. Okay.
So that's okay. In metric,
So thing we ever written as -1 a square should contain k.
that is actually not true. You are right. That a square minus a square, 1 minus 1 a square is not true. If I use k not equal to, that is only true for k equals to 0.
Okay. Yeah.
I just use simple form, but
Okay.
you are right. Actually, it should happen is that the dr square part will contain 80 square by 1 minus k.
1 minus k square.
But theta and phi, they will be 0.
Okay.
Not 0, just 8 square t.
Okay, sir.
Yeah, got it? Yes?
Yes, yes.
Okay, so now as you have the equation for k equals to 0, you have the equation. Okay, so a dot by a square is just 8 by g by 3 rho. Now, as I said, though it is rho total means what? Mainly three things. One is rho matter, another is rho radiation, another is rho dark energy. or cosmological constant. We'll come to know that very soon. So when I say you are in matter-dominated universe, that 8 billion years in the between, you can easily ignore these other two. Okay? When I say you are in radiation-dominated, you can ignore these, and you get only 1% error, or not even that, because cosmology is a long duration. So when they dominate, they really dominate in their epoch. They are almost like 100%. Okay, only when you move from one epoch to another epoch, in the transition time, the components should be kept. But most of the time, you get a good solution. So now I tell you that from last class, I know how raw matter goes as a function of scale factor. Can you tell me how raw matter goes? Some rho naught by
Q.
AQ.
A square,
Q.
a cube, volume, no square, okay? Now rho radiation, Ravi, you should not tell, you know that. Other people?
A power 4.
8 power 4
1
divided
by
by
8 to the power. And for rho cosmological constant or dark energy, we will come to know, or cosmological constant. How much?
It's constant. Right?
It's a constant, lambda. It does not depend on A. So now take your pen and paper, and I say that in this all dominated universe, suppose it is in the matter dominated, then you can neglect the other two. So in this part, find out from the above equation, solve for A T as a function of T. Can you do that? It's a simple two-line differential equation. Two-line solution of a simple differential equation. Please solve that. Use the above derivation we did last class. Once you get your answer, you tell me. Or message in the chat. Once got it, you tell me. I want the function time. Function, how does it go? You are doing it, no? Right? No, Gauri Shankar, that is wrong, because I have given you rho as a function of A. Rho is not independent of A. That's why I have written it down already up. You have to use that. That's why you get exactly function of time.
For matter, is it like T power 2 by 3?
So who is saying that?
Jahank.
Let me see what you got. AT equals to goes as T to the power 2 by
2 by 3.
So the answer is right, but other people also do it. Aram said it's very easy. Okay, so you have to put rho m is rho naught by a cube. Ravi, you got the answer?
Yes, sir.
T to the power 2 by 3.
Yes.
Gauri Shankar, you missed T term because I asked you to how to get a function of time. So please put rho naught by a cube. Yeah, good. Okay, T to the power 2 that will be there. Good. Other people? Other people? Everybody got it? Who have not got it yet? It's very easy. Srivardhini got it. Other people say yes or no. Jahan got it. Avinash? Got it? Okay. Very nice. So now, for radiation, do the same thing. It will be faster now. I give you 1 by a to the power 4. Do it for radiation and then do it for cosmological constant. I want these three. Function of time. How the scale factor changes with time in different dominated universe. Because then you can find out the acceleration or rate of expansion of the space. Once you get for radiation, tell me what is the answer and then do it for lambda to the power 1 by 2. To the power of half. That answer is right. Okay. Now do it for constant, rho dark energy, cosmological constant. Exponential some constant होने चाहिए, ठीक है? Some lambda times t. Yes, the rest of the people do it. It's very easy. Some constant or something. Yeah, 8 pi g lambda by t. Constant times t. Other people got it? Once you get it, then just say yes, sir. Then these are the simple things you need to do. Yes, Gauri Shankar got it. Srivardhani got it. Ravi?
Yes, sir.
Okay. So now you all tell me that which dominated universe expands fastest?
Dark energy dominant.
Dark energy dominated exponential expansion means when you put an energy in the right hand side of the universe, in the cosmos, a constant energy density which does not change. That means which is related to the emptiness or vacuum. So that's why dark energy is not the energy of something, because if it is energy of something, it will dilute. because if it expands in energy, but if it is energy of nothing, the space is becoming more and more nothing because it's expanding and energy is increasing. So that's the whole idea of cosmological constant. And in radiation, it dominates slowest expands, and in matter dominated, it's faster than radiation, t to the power 2/3. So starting from Big Bang, I show you that picture. That is the expansion of space. It was up to this is t to the power 2/3. Then in between is, sorry. What is the first one? Tell me. Radiation dominated universe. How much it will be?
Root
To the power. How? Radiation is the earliest. No, this is the Big Bang.
e to the power 1/2.
1/2. Very nice. This is t to the power. Tell me. 2/3.
3.
And this part is exponential. Constant. So at present, universe is actually blowing up. This is the space is expanding. Middle May, it was faster, and radiation, it is the slowest. So it is other way around. When the Big Bang happened, it is not like a burst though, because we don't know, but I'm just telling Big Bang. Actually, the space was expanding slow. Then it picked up. Then it picked up very fast. So it's completely contradictory of what we thought. Okay? So now let's go a little bit more deeper into it. So what is the second Friedmann equation? Second, I'm just writing FR equation. Can you tell me the A double dot equation?
A double dot by
Pick it out. Huh?
A double dot by A is equal to
Equal to
minus 4 pi G by 3.
by 2 nahi.
3
By 3.
all multiplied by rho plus 3p.
Very nice. Who spoke this?
Gauri Shankar.
Okay, very nice. So this is everybody got it, this equation. Now I'm going to do something amazing with this. So now, let's go to the right hand side a little bit. This was the discovery by Hubble. You all know that. Velocity versus distance in the space. He got it as straight line. That means it is proportional to h. And this doesn't look proportional. This looks like a Lagrangian. Anyway, proportional to h. So that means v equals to hd. Now in space, generally v is, because the expansion is due to the expansion of the space, not their own velocity, because it is going in every direction. So v is kind of a dot and d is kind of a. So this is just this. So you can know now a dot by a is basically h. The same Hubble's constant actually enters in the a dot by a. So the first Friedmann equation, sometimes in Planck unit, people write it like that. Planck unit means natural unit, where you take a G, C, all this thing to be 1. That is your homework. Study the natural units of particle physics. It's very easy. With that, I'm writing the same equation, 3a square m Planck square, the first Friedmann equation, is equal to this. M Planck has all this 8 pi g by 3, all this thing comes here, okay? And it becomes rho matter plus rho radiation plus rho lambda. This is a better way to write. Now these things are, we know, if you write a dot, then it goes as a cube. And if you write a dot, that is a constant by a to the power 4. And this remains like rho lambda log. Clear? This is another way of writing the Friedmann equation in. But anyway, so now this is kind of like this V is equivalent to A dot, and this D is equivalent to A, because A is the A means the expansion. A is kind of a distance is basically D is basically some lambda times A, constant times the expansion. So that's why A dot by A is H. Now, what we saw 20 years back, a physicist from Berkeley in USA and other university, Johns Hopkins University, they actually saw that it is actually here curving up. Then as you go to higher distance, it is curving up, and then it becomes linear in small distance. So it deviates from the linear thing going up. That means the universe A double dot is actually greater than 0. This is very abnormal because it came as a shock to people when they found. What does it mean? It's something too different. Mathematically, what does it mean? I will tell you. But physically, A double dot greater than 0. This is just an observation, and it got the Nobel Prize. Got the Nobel Prize because this means something unbelievable for our universe. A double dot 0 means it is like that. Suppose this is Earth. This is a tree. I'm drawing another tree. Now you throw a ball up. The ball goes up, and it's slow down, and then at some point it turned back. This is the ground, okay? This is the ground. It turned back. This is what gravity does. It slows down the space, and we were thinking that that it was the case for expansion of the universe, because nobody knew this rho lambda term is at all there, because it cannot be seen in eyes. It's a vacuum energy. Nobody has seen it. Only way we found it out that it is there by finding out A double dot. So nobody knew that even A double dot will be greater than 0, because all we knew from our standard model when they were doing the experiment, they didn't want to discover it. They just wanted to verify the Hubble law here at to high distance. But what they got is shock, that when they see very far away supernova galaxies away from us, they found out that supernovas are actually accelerating. Instead of going V equals to HD at a constant rate, this Hubble law does not work, that it is accelerating. So here A double dot by A is a constant. No? So sorry, A dot by A is a constant, and in this Hubble law, if you do A double dot by A double derivative, it will be 0. That is Hubble law, but they found it non-zero. Which means an apple was going up or a ball was going up. It is exactly like that. And one day you throw the ball and suddenly you see it accelerate up here and vanish from the space and go away. It become more than escape velocity, and it never. So if that thing happens to you one day, you throw an apple and the apple never comes back to your hand, know that that is equivalent to finding out dark energy, because that is what exactly happened. The space is slowing down. How do you know space is slowing down? Because you can see that T goes as T to the power 2/3 in matter-dominated universe. Yes. So A double dot, how much it is positive or negative? Can you take pen and paper and do it for T to the power 2/3? You have already find out.
T to the power minus 1 by 3.
A double dot. I
T to the power.
want a sign, positive or negative. I don't want the value. Negative sign, positive. Huh?
It will be negative, right?
It will be negative. That means it was decelerating. Yes. So it is an expansion universe, expanding universe, but A double dot was less than 0 for matter dominated 8 billion years. Is it clear for everybody? Or shall I repeat it? Expansion means space is stretching, but it is slowing down. But still, when you are driving a car, even if when you put a brake, still you are moving ahead, but you are slowing down, isn't it?
Yes, sir.
Exactly. You have to say yes or no, otherwise it feels like
Yes, sir.
yes. But what we found that after matter-dominated era, in fact, that's how we define that there is a dark energy-dominated era. We found that this actually flips and it becomes at a point when A equals to AC, a critical point. We'll know it later how much it is. A double dot flips and it will become greater than 0. So almost like Apple was slowing down, slowing down. At some point, blows up into the space. So what is this that gives a repulsive gravity? Because attractive gravity will make it slow down, but you need a repulsive gravity. And that is dark energy. And how do we know that? That I'm going to do it now. It's very easy. Take the second equation, A double dot by A equals to minus 4 pi G by 3 rho plus 3p. It can only happen for A double dot greater than 0. What we need? Rho plus 3p is how much?
Negative.
Minus 1. Sorry, rho plus 3p is less than 0.
Less than 0.
Which means P by rho is less than minus 1/3. You remember last time we defined W, which is ratio of definition. P by rho is actually less than minus 1/3. What observation found? Observation that W equals to minus 1. That means P pressure equals to minus rho. This was actually found by Einstein, but he didn't know about dark energy. He said there is something called cosmological constant, vacuum energy. T mu nu is lambda times G mu nu. If you have this metric, that is your homework. If you have a T mu nu like this, okay, then find out that P equals to minus rho. Homework. Is it clear, the homework? Yes, for a cosmological constant metric like this, T mu nu, show that P equals to minus rho. So it is different than the matter fluid or radiation fluid. For matter radiation fluid, it is P equals to, for matter, W equals to 0. For radiation, so W equals to 1/3. Clear? Because P is equal to 1/3 rho and P equals to, we discussed it in the last class. So this thing I'm taking it little slowly to you, but now you know that to have an accelerated universe, A double dot greater than 0, which they found from Nobel, they got Nobel Prize for, it's observation. We need W we find close to minus 1, not exactly. We found it like minus 1 within the error bar of plus minus 1% or 2%. Actually 3%. But we want to narrow it down with next generation experiment to less than a 1%. So this is a huge question. Why, I'll tell you later. That finding out W of dark energy, whether it is minus 1 or it is a little bit different than minus 1, because acceleration can happen when it's less than minus 1/3. But if it is minus 1, exactly, that means it's a cosmological constant, CC. That means its metric is like that, and this is called vacuum energy. In field theory, this cosmological constant is equivalent to quantum mechanics. Quantum mechanics may, when you do simple harmonic oscillator, what is the energy of, can somebody tell me, of different level? En. So the lowest energy of energy when there is no movement, oh, sorry, again the semicolon. Lowest energy is not zero in quantum mechanics, but in classical mechanics, when there is no movement in a harmonic oscillator, when the kinetic energy comes to zero and slowly, then lowest energy E can be zero when both Ke is equal to zero and both P equals to zero in classical energy. But in quantum mechanics, it can never be. The lowest energy is always half H cross omega naught. So quantum field theory means it is nothing but each point in space there is like a vibration, harmonic oscillator, vacuum energy. Vacuum is oscillating in each point. That is the whole idea of quantum field theory. That means it is like an ocean, and particle can be created like in waves anywhere. It goes up. Waves got created in the ocean, and waves comes back to nothingness. So here also you have a dagger annihilation and creation operator in quantum field theory. So in quantum field theory, the particles are not particles. Particles are just the vibration of wave packet in different points. They travel and then they back to zero. That's what happening every day in LHC in CERN, where the God particle Higgs was discovered. You collide, you create such wave packet of Higgs, and immediately it vanishes to zero. So that means there is a field underlying with non-zero energy called the vacuum energy, which is not zero. So not zero means what? Here in quantum field theory, you have to basically sum over H cross omega naught of I 1 to m. I mean, there are many infinite, and there is a proper way. I'm just giving a naive idea, because quantum field theory is a 2-semester course in any graduate school if you want to do particle physics. Okay, so if you do a proper integral with all these things, then you get the value of rho equals to lambda, and you get exactly it is minus the pressure P. This is the outcome from quantum field theory calculation. So now, once the dark energy community, or not dark energy, the cosmology said that there has to be A double dot is greater than zero and W has to be less than minus 1/3, then this is from observation. Then the theory side of QFT, big, strong, very like Edward Witten, like Einstein's of modern time. They said, yes, we have a candidate of lambda rho vacuum, because we are living on an infinite reservoir, and so our world is infinite. Nothing is not nothing. It is just the ground energy of infinite energy. On top, the excitations are basically this physical world, and that rho vacuum, which is the ground state of whole quantum field theory, they can calculate it theoretically, and they found its value. I'm calling it rho naught lambda theory. Now they want to match. Once you calculate from theory, you want to match because you exactly can calculate rho observation of dark energy from experiment. Why? Because not only a double dot is positive, you can also measure a dot by a square from the supernova experiment, and that you know that it is proportional to rho lambda. So you know how much rho lambda you need to get the a dot by a in that distance. Not only that a double dot is positive, but you can also. So they found out that is rho observation. Okay. Now they wanted to match, and then when they wanted to match, they found something amazing. You know, do you know that once you find something from experiment and once you find something from theory, they should match? Yes, for a good theory, right or no? Wrong? Yes or no?
Yes, yes, sir.
Yes, sir. So they wanted to match because this is the only candidate we have which has negative pressure, and this also because there is no other thing has negative pressure, rho minus p, that is the vacuum energy. Okay, negative pressure, all the thing match, but then they wanted to match the value, and then they wanted to match, and they found this thing, rho naught theory of lambda is approximately so how much order higher?
This is very large.
Huh?
10 to power 120.
I did not make a typo here. It is the biggest mismatch in the history of physics. The theoretical value of dark energy, the top Nobel laureate physicist calculated, and they found it 10 to the power 100 times higher than the experimental value. So these question that why rho experiment dark energy is 10 to the power minus 120 times rho dark energy theory. This is called cosmological constant problem. We don't know. This is still a mystery. And there is no answer to this. And it is not a normal number. It is how much? 10 to the power minus 120. So got the point? Yes or no?
Yes, sir.
So now some people will say, so what matters? Why it matters that maybe minus 120 or minus 115 or minus 110? What does it matter? Let the theorist ponder about it. Anyway, we got a value. Anything can be a value. As long as rho vacuum is constant, we'll get an exponential answer, exponential expansion, and we'll match it. But that is not the answer. That is it is much more deeper than that. So now I'm going to do that, and this is really very, very interesting and philosophical. That I told you that first starting from the Big Bang, this is the radiation dominated era. RAD, radiation dominated era. That means TA was going as T to the power how much? Half. Then matter took over, that we know from last class, 1 by A cube, and it has to take over. Then matter took over. It is around, say, 0.1 million year. Million, oh, sorry, again, the same. There are a lot of buttons here. Million year. Then from there, this is around 8 or 9 We don't know exactly, but we know 8 or 9 billion years. That is the time actually Earth was formed. Earth, Sun, everything. Same time, solar system was formed. And then from there onwards, the space has started going exponential. So e to the power lambda t, sorry. And here in matter-dominated era, how space was going? E to the power?
2 by 3.
Very nice. So now there is something amazing that we'll do in the last class. Ravi is working, Ravi knows that. It is called perturbation theory. We'll come to that later. But right now, just know that galaxy can only form in this matter-dominated era. You cannot form galaxy in radiation because its radiation has an outgoing pressure. As we said, it is 1/3 P, 1/3 rho. So you can never make a galaxy of photon or very highly relativistic particle because they are moving so fast. Is it right? Yes? Yeah?
Yes, sir. Yes, sir.
And also, right now in expansion universe, when space is stretching things so up fast, gravity is trying to pull the gas into galaxy, but the space is stretching it exponentially and you cannot form galaxy. Then you might say, but doesn't that mean that last 4 billion years there is no galaxy formed? Yes, formed, but it has formed where already things has collapsed, means in a small distance. As I say, the expansion of the universe can only be felt in a very large distance. If you are on a balloon, and this is the balloon surface, and balloon is stretching very fast in all direction, and ant at a small distance will not feel the expansion. But if somebody is here and somebody is here, and if they measure the distance, they will see that they are going away very fast. So that's why intermediate galaxy or chota galaxy cluster, they are out of this expansion. They don't feel it because they are already separated from the expansion. Gravity has already won over it in matter-dominated era here. So the gravity has already collapsed them and they are under their own forces. But large distance where gases wants to come and form gravity, it is not possible in dark energy dominated universe because in large distance the expansion is going very fast now and going away and you cannot collect gases to form galaxy. So that's the idea. New galaxies in large distances where space has already under this accelerated expansion of dark energy, large distance, you stop forming galaxy. And then more you wait, as the expansion is high and high and high, it will start stretching over the small distance, and slowly galaxy will also get affected by the expansion because it is an exponential expansion. It will slowly take over the space more and more and more. And at some point when it will come, this is our Milky Way, this is Andromeda, this is some other galaxies, they will move away from each other. Then intergalactic distance will be very much infinity or very far, you cannot see them. So you will only see that our Milky Way is holding there. If you come 4 billion years later, take a rebirth, you don't have to believe rebirth, I'm just kidding, and say you are an astronomer 4 billion years later and you are in IIA or Pondicherry University, you want to find out what is up there in the cosmos, you find nothing. Because everything has stretched into the expansion of universe into the infinity. Space is taking over. So, right now, in this 13.7 billion years, this time when we are, because if you wait for another 4 billion years or 5 billion years, then you will see things will move apart. You will end up in an empty universe. But right now, this time, where we are right now is the most fascinating times in the cosmos because cosmos is revealing all the galaxies, everything it has formed recently in cosmos time, few billion years back, and now they're in their all glory. And that's why with our SDSS, galaxy survey, we have found billions of trillions of galaxies far away. We have found magnificent picture, most beautiful pictures of formation of galaxy, their birth, billions of their number, how they are making a filamentary structure. It is like a Diwali going on, firecrackers. Most beautiful time is now. But if you wait for a little bit, you'll find nothing. But that's not the problem. The problem is now what I'm telling is even more serious, that why the mismatch really matters. So now this is the boundary where dark energy took over. Now you tell me, if the number is instead of 10 to the power minus 120, if it is 10 to the power minus 115 times rho theory. Say, as it doesn't matter, let's increase it 5 orders, because anyway it's a huge small number. Then this transition line will move to the left or right? Who can tell me? Dark energy domination will start earlier or before? If you increase the value of dark energy. You got the question? Yes or no?
Yes, sir.
So tell me, yes, if you increase the value of dark energy, rho lambda by 5 order of magnitude, this is the time, no? Left side is early, right side is later. So this line will move left side or right side? The dark energy domination. Not sure? Right side?
We are increasing dark energy in the sense.
Remember this line, this is the matter, this is the radiation, sorry, this is radiation, sorry. Let's draw it nicely. Before, yes, so so it is, this one is my radiation, 1 by a to the power 4. This one is my 1 by a to the power q matter. So this is matter radiation equality. Now this one is my rho lambda. So it takes over at this point. And we stay here now. This is now. So this is the dark energy dominates over matter. So now you see, if I increase it a little bit more, then it will move left side or right side?
Left side.
Now it is clear. See, I am increasing it a little bit more. So you can see the cross happens a little bit here. Yes? Clear? Yes or no?
Yes, sir, clear.
Yes, sir.
So now, if you take it, say 10 to the power minus 115, because actual value is 120 minus. So 5 orders, if you increase, you will see that you move like here, pretty much here. So you cut down the matter-dominated universe, smaller and smaller, isn't it? Yes.
Yes,
And I
sir.
told you that the matter-dominated universe is the only time where the galaxy can form. In fact, it is shown that most of the galaxies actually form here, later part of the matter-dominated universe. These are the time when you are actually seeding up the galaxy formation. So if you, instead of 10 to the power minus 120, if you go, say, I am giving you exact number, it is like this, 0.00000000000000001, and you just erase 1, 2, 3 zeros. It's like it doesn't matter. Anyway, so many zeros, as theory and experiment doesn't matter. But if you erase 3 zeros, it can be shown that you will be erased 2. That means life can come. Anyway, life came much later. No galaxy could be formed. If you just take life, and then even you can show that minus 113. If you just erase by 2 zeros, you can show that a human cannot be there. So it is a very philosophical question that this fine-tuning, because fine-tuning means what? When we don't know the value, why it is so much less. So lambda observed 10 to the power minus 120 lambda theory is such a nice fine-tuning. Putting so many zeros is needed for life to exist. Now this creates a huge turmoil in the society, physics society. That means whether universe is fine-tuned with some unknown vacuum energy so that we can all be here and do physics and enjoy life. Because there is no natural explanation till now that why this value is so small. And this is called cosmological coincidence problem. So first problem is cosmological constant problem, that is like why the two does not match. And the second problem is more severe. Okay, it doesn't match, but does it matter whether it match or not? Maybe 1 zero less or 2 zero less. Answer is yes, it matters. So this is what is called cosmology, and it is still a mystery that why dark energy. So clear? Getting clear? Yes? That cosmology, because this is the point, that if you start here, then from here only you will start e to the power lambda t, and you cannot form galaxy. You need t to the power 2/3. A very delicate balance happens here that if we get time, we'll let you know towards the end classes, that for this kind of fraction of space accelerating, expanding, gravity basically wins over the expansion and matter can clump into gravity. Okay, so this is the existence of dark energy. And now I will show you a video. You can all turn on your camera. In the meantime, I am showing you a very nice video of my PhD advisor, Professor Brian Green. It's a TED talk about what I said. Let me see. Okay, it's a very nice talk given by TED about dark energy. I'm just going there. Just wait for 30 seconds. I'm scrolling to exact minute where this dark energy he talked about. Okay. Just one second. Yeah.
In part one, here it is.
Let me share the screen. You can see? Yes, screen?
Yes, sir.
Okay.
When the astronomers worked out how much of this dark energy must be infusing space to account for the cosmic speedup, look at what they found. This number is small. Expressed in the relevant units, it is spectacularly small. And the mystery is to explain this peculiar number. We want this number to emerge from the laws of physics, but so far no one has found a way to do that. Now, you might wonder, should you care? Maybe explaining this number is just a technical issue, a technical detail of interest to experts, but of no relevance to anybody else. Well, it surely is a technical detail, but some details really matter. Some details provide windows into uncharted realms of reality, and this peculiar number may be doing just that, as the only approach that's so far made headway to explain it invokes the possibility of other universes, an idea that naturally emerges from string theory, which takes me to part 2, string theory. So
this part I have omitted. There is one explanation, but that is not at all a worked out explanation. People are speculating that from string theory, they give multiverses, means our universe is not the only universe. And they predict this value of cosmological constant of vacuum energy or 0-point energy should be different in different universes. And they showed that out of maybe 1,000 crore universes, one universe should have value of 0.013, like a probability. And we luckily be in one of them. So this is really amazing in the sense that we have been here in life. It's also a magical thing from perspective of physics. It is not so natural that everything will create life. Now, last part, okay, that I said, what will happen to the future of the universe if dark energy dominates?
intense that as space rapidly expanded, tiny quantum jitters from the micro world would have been stretched out to the macro world, yielding a distinctive fingerprint, a pattern of slightly hotter spots and slightly colder spots across space, which powerful telescopes have now observed. Going further, if there are other universes, the theory predicts that every so often, those universes can collide. And if our universe got hit by another, that collision would generate an additional subtle pattern of temperature variations across space that
this part we have not talked, but if there is a chance that one universe bubble can collide one universe, if we are lucky, then we can see them in cosmic microwave background that I was talking about, because it is a global fossil radiation coming from Big Bang. So if some other universe has collided in one side, it will get distorted in the space. Anyway, that I just told you that multiverses are under search, but we cannot see the multiverses because of our limitation of Einstein's special theory of relativity. That we cannot see something which is beyond our horizon, as we have talked about already. Next class we will exactly calculate the value of our horizon. That is the highest we can see. So if there are other multiverses beyond that, we'll never see. But if once multiverse has collided with us, luckily, some part age colliding with another age, then we may, but that we have not seen it till now. But now,
because the expansion is speeding up, in the very far future, those galaxies will rush away so far and so fast that we won't be able to see them, not because of technological limitations, but because of the laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black stillness. And they will conclude that the universe is static and unchanging and populated by a single central oasis of matter that they inhabit, a picture of the cosmos that we definitively know to be wrong. Now, maybe those future astronomers will have records handed down from an earlier era, like ours, attesting to an expanding cosmos teeming with galaxies. But would those future astronomers believe such ancient knowledge? Or would they believe in the black, static, empty universe that their own state-of-the-art observations reveal? I suspect the latter, which means that we are living through a remarkably privileged era when certain deep truths about the cosmos are still within reach of the human spirit of exploration. It appears that it may not always be that way, because today's astronomers, by turning powerful telescopes to the sky, have captured a handful of starkly informative photons, a kind of cosmic telegram, billions of years in transit, and the message echoing across the ages is clear. Sometimes Nature guards her secrets with the unbreakable grip of physical law. Sometimes the true nature of reality beckons from just beyond the horizon. Thank you very much.
Right, thank you.
Okay, so now a little bit of philosophy and this thing is
Incredible.
interesting. Yes.
How do you?
Yes. So this is the dark energy. What we discussed today, that people are still working. I am also working. Ravi is also working. One of such model. And next class we will actually calculate the size of that horizon, how much we can see when the space is expanding with some mathematics, and then we'll tell you two basic problems of this Big Bang cosmology. Till now, I have been talking about Big Bang cosmology, but later we'll see that it is wrong. Means the idea that universe started with a hot plasma and then matter dominated, then dark energy, will not be able to explain something which we see in the cosmos. So what is that? That is called inflation. That means we came to know from observation that there has been another dark energy domination in the beginning. So there has been another exponential expansion in the beginning, then radiation, then matter, then again another dark energy. So these are very fascinating, and we'll next class, by doing simple mathematics, we'll come to know that why we found out that there has to be another dark energy domination in the beginning. Okay, good. So before we end today, there is one homework I want to give you.
Sir, I have one question.
What is also better is to do some mathematics.
Hello?
So the homework is this. The two Friedmann equation 1, I will not write it again, and 2, a dot by a square and square. Another is a double dot by a. You know that. Using these two, there is a third equation, which is not an independent equation, but many times useful, is called continuity equation, which we have actually used, but you don't need to know that. Just find out that, derive this equation, d rho dt is 3h rho plus 3p. So basically, take these two equations. Here you have rho total, so you have to take a derivative, d rho dt. Okay, and then you have to take derivative in the left hand side. You will get two terms. Use the second equation, put it back, and find out this simple equation. It is true. It is not an independent equation. It is equation number 3. So if there are a system of equations which are not independent, any two of them we can use because they are independent. So sometimes we will be using these in cosmology, sometimes we will be using these two, sometimes we will be using these two, or sometimes we will be using these two. So this is your homework. Show that d rho dt is 3h rho plus 3p. Okay, clear? Okay, great. So send me the homework. Avinash has sent me last week's homework also. So whatever I discuss, I will not write down the homework for you. You have to be attentive enough. I will not grade, but this homework, if you do, you will do very good in the exam, as well as you will understand. Okay. Good? Okay.